Hello everyone, I'm Mao Zhou from Beihang University. Today I'm going to present our work, Graph Neural Networks Automated Design and Deployment on Device-Edge Co-Inference Systems. Here is the outline of my presentation. The first part is our research motivation. Graph neural networks, GNNs, have been widely applied to various graph-related applications, such as recommendation systems. In addition to these cloud-side applications, GNN is also becoming popular in many device-side applications, such as point cloud processing. But compared to powerful cloud devices, edge devices often have limited computing and memory resources. This limitation is particularly challenging for GNNs, which are known for their complex computations and high resource demands. Deploying GNNs on such resource-constrained devices for real-time inference faces significant challenges, such as high latency and energy consumption. For example, even the hardware-efficient GNNs searched by HGNNs achieve only 2 frames per second on commonly used Raspberry Pi, which is far from meeting real-time requirements. This highlights the need for a more efficient deployment strategy. And with the wide application of AI in real life, device-edge co-inference has emerged as a promising paradigm for the large-scale deployment of AI applications in edge scenarios. In this paradigm, mobile devices capture raw data and conduct pre-processing, then send intermediate data to edge server for collaborative computation. This approach can greatly improve efficiency and save energy. And the key to maximizing the benefits of co-inference lies in partitioning models into computation-friendly and computation-intensive parts across the device and the edge. So, how do we select the optimal select point for GNNs to achieve the best system efficiency? This is a problem we want to explore in this work. And our research is driven by 3 key motivations. The first one is exploring the trade-offs between computation and communication in device-edge co-inference systems. When choosing a stability point, we need to consider 2 main factors: the computational efficiency on the device and the communication overhead. We experiment with different split points in the popular point cloud processing model DGCN, and we found that splitting after the last pooling layers results in minimal data transmission but leads to a high workload on the device. Conversely, splitting at the first KN layers reduces the workload on the device but introduces additional data transmission. Therefore, selecting the appropriate split point requires a balanced consideration of network condition and the device's capabilities. The second motivation is perceiving the heterogeneous hardware sensitivities of GNNs. We conducted experiments on various edge devices and found that the same GNN model performs differently and encounters distinct performance bottlenecks depending on the device. Each type of device is better suited for handling different GNN operations. Therefore, when designing and partitioning GNN models, it is crucial to consider the hardware sensitivities of both sides to fully leverage the potential of co-inference. The third motivation is addressing the gap in automated design and deployment of GNNs on device edge hierarchies. We experimented with the potential optimal partition schemes for DGCN and found that the improvements in efficiency were very limited. So, in practice, partitioning existing GNN models and deploying them on device edge co-inference systems often fails to achieve the expected performance improvements and does not fully leverage the potential of this paradigm. And unfortunately, research on GNN device edge co-inference is still lacking. HGNNs and MagNNs have attempted to design efficient GNN models for edge devices using hardware NNs, achieving some acceleration, but they did not consider the communication overhead. On the other hand, branch GNN tried to manually select split points for existing GNN models, but did not explore novel architectures, resulting in limited speedup. In practice, this approach does not fully leverage the potential of the device-edge co-inference paradigm. We believe the fundamental reason is the detachment of architecture design and co-inference partitioning. Therefore, we are motivated to design the GCoDE framework to jointly optimize in architecture and co-inference schemes. Next, I will introduce our proposed GCoDE framework. Firstly, the input of G-code includes several user requirements, such as optimizing metrics like latency and energy. The key component of G-code is the joint optimization of architectures and mapping. We developed a unified design space that allows us to optimize architectures and the corresponding mapping schemes across device and edge at the same time. By leveraging a constraint-based search strategy, G-code can quickly find the best architecture mapping pairs. During the search process, system performance evaluation of these candidates is based on our prediction method, which avoids costly on-device measurements. And another important component is the device edge deployment tool. It provides an efficient co-inference engine that supports the automated deployment of the optimal GNN architecture and mapping candidates across the target system. Next, let me explain the details of the co-inference design space. The primary difference between co-inference and single-device inference lies in the data communication between the device and the edge. To achieve joint optimization of architecture and mapping, G-code is based on a novel perspective, treating communication as a special operation. Therefore, G-code extends the GNN architecture design space by abstracting communication as one of the explicit operations. So, the GNN architectures assembled within this co-inference design space inherently include their operation mapping schemes, as shown in the figure. Each communication operation in the architecture represents a partition point. In this way, G-code can find the optimal architecture with its corresponding mapping scheme in a single search process. On the other hand, this special design space also brings some challenges to the exploration process. Each sampled candidate may include invalid configurations. For example, two consecutive communications are minimalized. This can result in a large overhead on identifying valid architectures rather than focusing on higher performing ones. So, a more efficient search strategy is needed to improve the search efficiency. To address this problem, G-code uses a constraint-based search strategy. In the first search stage, G-code tries to identify the optimal operation size with a random search method. This process involves 4 steps. And firstly, it will randomly sample operations to generate GNN architectures. And second, a constraints check will conduct on these architectures, including validity and system performance evaluations. Only architectures meet the requirement are then evaluated for accuracy and final scored. And then based on these scores, G-code will update the candidate optimal architectures. This process will repeat until we get the expected result. After identifying the optimal operation site, G-code performs scale-down tuning on the corresponding functions to further improve performance. For example, it may try lower hidden dimension to simplify the computation. In the end, the optimal GNN architecture mapping pairs tailored for the target system is generated and ready for deployment. In practice, on-device performance measurement of candidate GNN architectures during the search process is time-consuming. Therefore, most search frameworks use specially designed awareness strategies to avoid real-time measurements. But it is even more challenging for device-edge co-inference. Due to various influencing factors such as system heterogeneity, network conditions, model structure, and graph data structure. To address this, we designed a predictor for efficient and scalable performance awareness. Specifically, by embedding the mapping scheme into the architecture, we can transform the performance awareness problem into a graph learning problem. So we abstract the GNN architecture and its mapping scheme as a special graph structure, where nodes represent operations and edges represent data flow. In this manner, we only need to learn the graph information to estimate the system performance. Given that the GNNs excel at handling such problems, we designed a GNN-based predictor to learn the architecture graph. For building the node features in the architecture graph, we combine the LT method and one-hot encoding. Each node's features include two parts: the model structure, encoded with a one-hot scheme, and the approximate performance measured by accumulating the latency of corresponding operations on the target platform, which is collected using LUT. This approach significantly enhances the node features. It better integrates the hardware sensitivities of target system into the graph. When performing system performance evaluation, we provide two options to adapt to different applications requirements. The first one is cost estimation. Since we have collected the latency information for all operations, we can obtain approximate performance through simple accumulation. This method is simpler and has lower overhead, but because it doesn't consider random overhead, the estimated value may differ significantly from actual performance. So it is suitable for scenarios without strict real-time constraints. And the second method is latency prediction. We construct a predictor based on 3 GN layers and with a global sum pooling layer to extract graph information. After carefully training and tuning, this well-polished predictor can accurately estimate the inference performance of candidate architectures on the target hierarchy. It is very well suited for applications with high real-time requirements. Once the desired gene architecture is found, GCoDE uses the integrated device edge deployment tool to deploy and execute on the target platform specifically. This tool includes a gene architecture tool to collect optimal candidates that meet different scenario requirements, addressing the ever-changing runtime environment. It also features a runtime dispatcher to dynamically adjust the deployment architecture for stable system performance. The computation process is based on our Co-Inference engine, built on the PyTorch geometric framework, providing efficient point-to-point gene co-inference. Next, I will introduce the evaluation results of GCoDE. GCoDE is implemented based on PyTorch geometric, and we have conducted various experiments on 4 different device edge configurations and on 2 different applications. The competitor includes several exciting works such as manually designed genes, GNNs framework, and gene co-inference method. For the point cloud processing task, GCoDE can achieve up to 34 times speedup compared to manually designed models and 9 times speedup compared to hardware GNNs frameworks. For gene co-inference approach branching, we achieved a 21 times speedup, which is attributed to the joint optimization of architecture and mapping schemes. And additionally, GCoDE also demonstrated better system performance in text processing applications. Compared to PNAS, it achieved about 6 times speedup, and compared to branching, it achieved about 14 times speedup. Will also significantly reducing energy consumption. Besides, our proposed system performance awareness method achieved high prediction accuracy across various system configurations. It can achieve 72 to 85% accuracy with 10% error bound. And compared to the gene hardware performance predictor designed by GNNs for edge devices, our method achieved a 54% improvement. Finally, I will make a summary of our work. In this work, we propose a system-aware automated framework for designing and deploying genes on device edge co-inference systems, named GCoDE. This is the first work to achieve performance awareness for genes deployed on co-inference systems. Additionally, we realized the joint optimization of gene architecture and mapping, achieving excellent speedup and on-device energy savings. That's all for my presentation. Thank you for listening.